You working in labs? Yes, sir, I have. You started working on it? Yes, I have met my primary guide only once. Yes, sir, I have. You started working on it? I have met my primary guide only. What fraction of the students are on campus now? Now mostly people are done. Very few are. First year, first year also. They haven't come yet. Yeah, but they can. In the new batch, I think there were only 9 or 10 students. Yeah, things are looking better in India, so I hope. Yeah. We are getting vaccinated also. In the hostels, we have to sort of maintain some social distancing and things like that. The bathrooms have been separated for quarantine and non-quarantine. Apart from that, we're not supposed to go to anybody else. So we are supposed to wear our mask as soon as we step out of the room. Some people are not more than it has been almost a year. So yeah. How long will people continue? Yes. Yeah, remember last year, end of February, I went to the US, which was cancelled. So it's just going to be about 1 year from there. Some other people also from our department had gone to the US, which had got cancelled. I don't know if it is the same conference. Probably the same. A lot of people. Many people from Onindo Das's lab went. So. Onindo himself, I think. Oh. It's a March meeting of the. Yeah, they have gone to the same. It's so sad for them. Because most people were in the final year, so they were really looking forward to the conference. We see also middle of March this conference in this. This year it's all fun now. Do you know any of the faculty that you have in Stevens? Not really. This every year, I guess this is held. Yeah. Yes. Would be alternate year, I think. Once it is organized by the economics. Because Dr. Popli, I think, shifted to economics later or something like that. I have forgotten. So two departments organize this. So probably that is the case. We are actually not calculating. There are two different electricity, so one of them is like that. Well, when we were in Delhi, I think Stephens was only for boys. Yeah, yes, yeah. And Miranda House was for boys. Yeah. Now Miranda House is still for girls. As it was.
Good afternoon, sir. Thank you for joining.
Good afternoon, everybody. Good afternoon. Sorry, you're muted.
Muted, yeah. Mic is muted, so you should.
I'm really sorry. So thank you everybody for joining in, and a very good afternoon to all of you. The Physics Society of St. Stephen's College is glad to welcome you all to the very first day of the annual Popli Memorial Lecture Series, which is a 3-day event taking place on the 18th, 19th, and 20th of this month. Dr. Rajendra Kumar Popli, also known as Dr. R.K. Popli, was an extraordinary teacher. He was never just interested in simply passing on the received knowledge to another generation. Instead, he himself was a creative thinker, and he constantly encouraged his students to think creatively. He was, in many ways, a very humble and simple person, moved primarily by a concern for his students and by the deep seriousness and sincerity with which he met everything in life. At St. Stephen's, he was widely loved and respected. To keep his memory alive, old students, friends, and the relatives of his have created a Popli Memorial Fund. This fund is used to organize the annual Popli Memorial Lectures. This year is indeed a special one, as it is the 25th annual Popli Memorial Lecture Series being organized by the Society. We are very glad to have Professor Chandan, Department of Physics, Indian Institute of Science, and International Center for Theoretical Sciences, Bengaluru, with us as our guest to deliver the lecture over the course of 3 days. Professor Chandan Dasgupta is an Indian theoretical physicist known for his contributions in condensed matter physics and statistical physics. He earned his BSc degree from Presidency College, University of Calcutta, and MSc degree from Delhi University. He did his doctoral research at the University of Pennsylvania, USA, under the supervision of Professor A.B. Harris, and obtained a PhD degree in physics. Subsequently, he did a postdoctoral research at University of California, San Diego, and at Howard University, and worked as a faculty member in the School of Physics and Astronomy of University of Minnesota for a few years. He joined the Indian Institute of Science in 1987, where at present he is a professor. Professor Dasgupta played a very important role in the establishment of Center for Condensed Matter Theory at the Indian Institute of Science in 1998 and acted as the convener for the center up until 2005. We are glad to have you with us here today, sir, and I extend a warm welcome on behalf of the faculty and students of St. Stephen's College. On behalf of our principal, Professor John Bergen, I request our alumna at IISc, Ms. Sandhana Bhattacharya, to present you with a case.
You can see us?
Yes, sir. Yes.
Okay. Okay. Thank you very much.
Thank you. Thank you, Ms. Nandana and Ms. Ronika. I now request our principal to speak a few words on this occasion.
Good afternoon and thank you. A few words it will be. This is the 25th anniversary of the Popli Memorial Lectures. And we are very privileged and honored to have with us Professor Dasgupta. So from college, let me say thank you for your time and for agreeing to come and share your knowledge and your experience with my young students here and also with the faculty members of the Department of Physics. We're very grateful for your time here. As you probably know, St. Stephen's College is a very small college, but it's a very special college. It's a very special institution because of the kind of people we have here, my colleagues and the students who worked so hard to get into this place. And today we remember a former member of the faculty who distinguished himself in two ways: his love for the subject and his love for his students. And his love for the subject is what propelled him to become such a successful teacher. And we want to continue that tradition of exemplary interest in the subject. And this year, we are very fortunate to have you with us. The young lady has said a few words about your professional background, but I'm sure that as you progress with your lecture, there will be much more interesting things that we will find out about you. I will not stand between you and the audience. Let me say thank you and welcome you on board. Thank you.
Thank you very much.
Thank you, sir, for your warm words. On this occasion, it is really appropriate for us to know about Dr. Popli and his legacy. I now request Dr. Jacob Therian of Physics Department, St. Stephen's College, to share a few of his thoughts on the same with us.
Okay, thank you everybody, and we welcome once again everyone who's come for this talk. So the students have asked me to share briefly a quick story, a true story about him, so that we get to see him a little bit clearer. And today I'm going to share a quick brief story about the last time he communicated to me orally. That was the last time I heard him speak, and it still fills me with grief. There are lots of nice stories about him because we shared the room together and we had the same office room together, and we miss him all the time. So what happened is one day I accidentally managed to pour boiling water on my left hand. And what do? It was very, very painful. I called Dr. Popli. Dr. Popli and Dr. Horace were extremely good medical doctors in homeopathy, and he discussed the symptoms and told me he'd send the medicine next day. So next day morning, I get a call from him and he said, I'm sending the medicines. You know, my hand was paining so much that I couldn't come to college. I had taken leave. And he said he's sending the medicine, but his voice sounded somewhat abnormal. And I asked Dr. Popli, are you okay? You're sounding a little distressed. And he said, Jacob, something is happening. The other teachers will tell you, but let's stop for a moment. And we stopped. Now, I didn't know that 2 hours before, the doctor had told him that he had got cancer of the throat. And somebody with a news like that would never think of calling somebody to give homeopathy medicines. And I was I'm still deeply touched by his thought for me. And that was the last time. The next time I met him, he wrote on a piece of paper that he had medically he was advised not to speak. And that was the last time I heard him speak on the phone. So we all fondly remember him. We remember his commitment. We remember his simplicity. And even though he was suffering, he was always ready to meet anybody. And I remember communicating with him. He used to write on a piece of paper, and we remember him fondly. So I just shared the story about the genuineness and the way he went out. He had gone and played badminton 4 days a week with another teacher who was in depression. And he was always available to everyone, be it staff or students. And we once again remember him very, very fondly. Thank you.
Thank you, sir, for your insightful words. Now, before beginning with the lecture, I would like to say about a few instructions that we have to follow during these lectures. First of all, I request all of you to remain muted during the entire lecture. And if you do have any questions, please type it in the chat box. And during the question and answer session, which will be held after the lecture, I will take up your questions and ask it to the speaker. And please refrain from, again, I'm reminding everybody, please refrain from unmuting yourself or any kind of producing any kind of stray noises. So without any further ado, I now request Professor Dasgupta to start off the talk. Over to you.
Okay, so I'll share my screen just 1 moment. I just get some glass of water.
Yes.
Just a moment. I'm trying to. Can you see my screen? Hello?
Not yet. It's not yet visible.
Okay. So let's see. So I'm trying to do this present now. Entire screen, window or tab? Which one works better?
Window, sir.
Okay. Now I see. It's come.
We can
Do you see it now?
Yes, sir, we can.
Yes.
Okay, good. So I'll make it full. Okay, so visible to everybody? Hello?
Yes, sir. It is perfectly visible, sir.
And you can hear me, right? No problem
Yes.
in the audio.
Yes, we can hear you.
Okay, so I'll start. So first, I'd like to thank the organizers of this lecture series for the invitation to give these lectures to the students of St. Stephen's College. It's a pleasure and an honor for me. The St. Stephen's College, of course, is one with a very, very good reputation, one of the best colleges in India, and has a very glorious history and all that. So many students that we see in our institutes are now coming from St. Stephen's College, and also many colleagues were studied there some time ago. So it's actually a pleasure and a privilege to be giving these lectures to the students of this college. I would also like to express my regards to Professor Popli, whose memory is being sort of celebrated in this series of lectures. From what I heard, he was a very good teacher. He played a very important role in the setting up of physics teaching at St. Stephen's College. So it's really a privilege for me to give some lectures that bear his name.
I had to Mathuri library book, then I had to pack. I was thinking about book. Let's look at it on YouTube.
Sorry, there is some somebody has to mute their mics.
Someone looking for like science block. I didn't know who. Are there other professors here?
Dr. Cherian, can you mute yourself, please, sir?
Okay, so then let me start my lecture. So there are, as everybody knows, there are going to be 3 lectures. And here I'm going to give a brief outline to the kind of things that I'll be discussing in these lectures. So the title of the talk is Emergent Phenomena in Condensed Matter Physics. I do theoretical physics, theoretical condensed matter physics. So I will begin with a very short introduction to condensed matter physics itself. I mean, what is it that we do, and what are the issues that are involved, and things like that. And then quickly I'll come to the main topic of these lectures, which is emergent phenomena in condensed matter physics. So I'll try to explain what one means by emergent phenomena. And there is this slogan that you sort of may have heard, some of you may have heard, it's called "More is different," which is basically coined by a very famous physicist, Phil Anderson, to sort of give everybody some idea about what these emergent phenomena are all about. So I will also sort of go into the kind of things that he said. There is a very famous paper in which this "more is different" meaning of that is explained. So I'll go a little bit into this. And then there will be the bulk of the talk, which is basically different kinds of emergent phenomena that we encounter in condensed matter physics.
In particular, I'll pay a lot of attention to a class of phenomena which are called phase transitions, and I'll try to explain why these phase transitions are thought of as emergent phenomena and what are the things that are interesting about this phase transitions and so on and so forth. And in particular, there is one aspect of phase transitions that I think is very important, involves some new concepts, and that is the spontaneous breaking of symmetries. And actually, this is the spontaneous symmetry breaking which makes phase transitions basically an emergent phenomena, according to the definitions that were given by Professor Anderson some time ago. So this is something that I'll spend some time on, and then various examples of phase transitions, which are of interest to condensed matter physicists. So I'll talk about some magnetic systems, liquid crystals, what conductivity, and so on and so forth. I think the first two lectures will be devoted to these topics, basically emergent phenomena, phase transitions, symmetry breaking, and some examples. And then the students asked me to also say something about disordered systems. So the third lecture will be on the statistical mechanics of disordered systems, and one kind of sort of new concepts, new methods, etc., are necessary to understand the properties of disordered systems. So, of course, I mean, I would certainly have preferred to give these lectures in person in Delhi. But of course, given the present situation, that is not possible. So one thing I miss in giving this sort of Zoom lectures, this kind of lectures, is that the questions cannot be asked during the lectures. So we just heard that you're supposed to, if you have questions, then please send them to the organizer, and then at the end of the at the end of 1 hour, we can have a discussion on those questions. So let's begin with an introduction to what I mean by condensed matter physics. Here we are basically interested in studying. For me, I do it theoretically, and many of my colleagues do this experimentally, to study various interesting properties of what I call matter, which I'll define to be a collection of large number of objects which interact with each other. So all of these things are terms that I have in this sentence are important. We have to have a large number of objects constituting the system that we want to study, and these objects will interact with each other. What do I mean by interact? That let's say, I mean, if I'm doing classical statistical mechanics, then the motion of one of these objects will affect the motion of some other object which are there in the same system. And these objects can be anything. So, of course, I mean, when condensed matter physics was first, the beginning of this subject, people were studying mostly properties of systems consisting of microscopic objects, the everyday things that we see all around us. And these microscopic objects typically are electrons and ions, atoms, molecules, things like that. So those systems, the objects that one is talking about, are these microscopic objects. But subsequently, condensed matter physics has developed in many other directions. And nowadays, condensed matter physics also consists of studies of systems which are composed of, let's say, mesoscopic objects, which are this, I mean, the examples are colloidal particles, polymers, and things like that, which are not quite microscopic, but still small, mesoscopic. And more recently, people have also started applying these ideas that one develops in condensed matter physics to collections of macroscopic objects. And again, various examples I have given. This could be sand particles, granular material, etc., etc. And again, very recently, people are also developing theories of the collective behavior of collections of living objects, let's say bacteria, fish, birds, etc., etc. This is called the statistical mechanics of active systems, which is a very important active area of research these days. So, I mean, you know, the condensed matter physics these days encompasses many different kinds of problems. The usual ones are standard objects that we see all around us. And then one can extend those descriptions, those methods, to many other systems where the constituting particles, so to speak, need not be atoms or molecules. They could be mesoscopic objects, they could be macroscopic objects, etc., etc. So, and this is, next line says, what I mean by interacting. It's basically the behavior of an object is affected by other objects. These interactions that will play a very important role in what I'm going to talk about later on. And in particular, this emergence phenomena, invariably, they involve interactions among the objects that constitute the system. And large number of also is important. I mean, large number, typically when one does theory, one talks about what is known as thermodynamic limit, which says the number of particles in the system is actually infinity. But of course, I mean, there is no real infinity in real life. So one has to have a large number of particles, and this emergence basically depends on having a very large number of particles. And this number that I have come up with, 10 to the 6, is basically arbitrary, because 10 to the 6 I say because these days many of these systems are being studied on computers, and in computer simulations one cannot of course simulate 10 to the 23 particles, Avogadro's number of particles, but then the kind of behavior that one wants to study are also seen in systems which are as large as, let's say, 1 million particles. So in that sense, 10 to the 6 is somewhat arbitrary. But what I want to say is that this behavior will be seen only when the number of particles in the system is very large. And since it is a large system, essentially, we cannot study it very microscopically. And there are statistical mechanics, many-body theory, dynamical systems. These are the disciplines that come into the picture when one wants to develop a theory of the behavior of such systems. So this is condensed matter physics in a transparency, in a slide. But I just want to give you some idea about what kind of systems that will be interested in. And this is something that many of you know about. So what I want to say in these transparencies is that there is one class of systems that we can understand everything, for which one can do the theory analytically, and everything can be deduced just by doing mathematics. These are systems which do not have interactions. So in the classical system, one basically has a classical set of particles which have some velocity, some forces acting on them, etc., etc. And we assume that there is no interaction among the particles. It's ideal gas. And there, as you know, everything is known about the ideal gas. Very simple equation of state, no structure, no correlation, etc., etc. What I want to point out is that when we don't have interactions, then the statistical mechanics of this class of systems, which basically consist of trying to understand the macroscopic properties of such systems, can be worked out exactly, and there are no surprises, so to speak, and everything is known, and one can work out everything. So the classical system is the equation of state is, you know about this, PV equals NKBT. If you have a Fermi system, now one is going into the realm of quantum mechanics. Again, one can work out the statistical mechanics exactly. And here I have written down the grand canonical free energy in terms of the degeneracies and the energies of the single particle states that the system has. And again, doing mathematics on this and taking derivatives and things like that, one can calculate all thermodynamic properties. And again, here you don't see any structure, any correlations, and some correlations. I mean, the correlations here, correlations basically mean that the motion of one particle affects the motion of other particles. And here the correlations come from Fermi statistics, the Pauli principle, that two Fermi particles cannot be in the same quantum state simultaneously. That leads to some correlations, but again, there are no surprises. One can calculate everything. If the quantum statistical mechanics is for a system which consists of bosons, again, that one can, there is the exact formula for the grand canonical free energy in terms of this degeneracy and the energy of the single particle states. Here, beta is 1 over kBt, mu is the chemical potential, etc., etc. And again, one can work out everything. As before, I mean, these systems also don't exhibit any structure. There is some correlation because of this statistics of the quantum statistics of the particles. And here there is a very special case that although the system is non-interacting, it undergoes actually this Bose-Einstein condensation, which is a very interesting phase transition. So this is one exception to the rule, so to speak. The rule is that if you don't have interactions, then you don't have any interesting behavior. But this boson, ideal Bose gas, is an exception to that, where actually one does see some interesting behavior at low temperatures in the form of Bose-Einstein condensation. But what I want to point out is that it's the interactions among the particles which make the problem interesting, and that leads to many interesting phenomena. And interactions are always present in real systems, but in some special cases, you can ignore the effects of interaction. Some other cases you cannot ignore. And what we'll be discussing is basically the effects of interactions in such a many-body system consisting of a very large number of particles, and the kind of emergent phenomena that arise from the presence of interactions. So this then brings me to the main, well, I mean, I can also give you some examples of interactions. This is something that you have seen in classical physics or in also quantum physics. Let's say if we have, let's say, a set of particles, then the total Hamiltonian of the system will have a term, which is the kinetic energy, P squared over 2m, m is the mass. And then there will be a term which tells us about the energy associated with the interactions, and I'm assuming pair interaction. So I and j are basically indices that represent different particles. And then you have a potential, which is a function of the Ri minus Rj. And, you know, this different systems will have different forms for this interaction term. I've given you some examples. The simplest one is what I call hard sphere interactions, where this interaction is 0 if the distance between the two particles is bigger than the diameter of each sphere, and interaction is infinity if the distance is less than the diameter. Interaction infinity basically means that two particles cannot come to a distance which is smaller than the diameter of each particle. So this is simplest. This is like basically billiard balls or something like that, where two particles don't interact when they're separated from each other, and they cannot come too close to each other, and the distance up to which they can come is basically is the diameter of individual particles. There are systems in which this kind of interactions are realized. Colloidal systems basically can be approximated as a system where this kind of interactions are present. Another interaction that you are all familiar with is basically this Coulomb interaction between two charged particles. So again, in that case, the potential function will have the charges qi, qj divided by the distance between the two particles in 3 dimensions. You may have also heard about screen Coulomb interaction, where instead of having this 1 over r dependence, there is in top of that, there is an exponential fall off as the distance increases beyond distance increases. Then, of course, this 1 over r also decreases as a function of distance, but this decrease is very, very slow because it's a power law. But then there are also screened interactions in which, in addition to this power law, there will be an exponential factor that will tell you that the interaction falls off much more quickly as compared to these long-range interactions. There are other interactions, depending on, again, which system you're looking at. There are always different kinds of interactions. And there is one interaction that plays a very important role, one kind of interaction that plays a very important role in many systems, like, you know, liquids and even some crystals, where the interaction has this particular form, that the potential is dependence on the distance has these 2 terms, 2 power law terms. One is power with 12, other is with the power of 6. And as you can see here, when the distance becomes much smaller compared to sigma, this term gives you a very large value. So again, 2 particles cannot come very close to each other, and there is a characteristic length scale, which is given by sigma. And so basically, this is the form of the potential, that if the 2 particles come very close to each other, the potential becomes very large and positive, which means strong repulsion. But then as you go to larger distances, then this term will dominate because it's a smaller power. And then this comes with a negative sign. So there is a potential well here. The strong repulsive interaction at short distances, intermediate distances, there is attractive well. And then eventually, as you go to long distances, this interaction goes to 0. So there are various kinds of interactions that one encounters in studies of this many body systems consisting of particles. Could be in some cases you can treat the particles classically. In some cases you have to treat the problems quantum mechanically. Quantum mechanically, you have to basically look at whether they're fermions and bosons. And then you have the Hamiltonian, which is the kinetic energy, and then there is the potential energy term, which we assume to be composed of pairwise interactions. And I've just given you some examples of such pairwise interactions that appear in studies of very common physical systems. So these are the kind of things that we'll be interested in. And the particular set of topics that I want to discuss today involves what is known as collective phenomenon or cooperative phenomenon or emergent phenomenon. There are many different names. And as I just told you at the beginning, the importance of such phenomena was in some sense brought into focus by a very famous physicist, Professor P.W. Anderson, got a Nobel Prize in Physics in 1977. And he wrote an article in this magazine, Science Journal, again, many years ago, 72. The title of that article was More is Different. And in this article, he sort of brought into focus the concept that if we have a large number of particles which are interacting with each other in a particular system, then there are properties of these large systems which are in some sense very different from the properties that you have for the individual constituents. So new effects, new phenomena, new insights, etc. arise when you look at the behavior of a system consisting of a very large number of interacting objects. And this is later on people sort of call this kind of phenomena that happens in these systems, emergent phenomena. Emergent basically means that if we just look at the basic Hamiltonian, for example, where you have some interactions among the particles, kinetic energy. And this Hamiltonian can be quite simple. And just by looking at it, we'll not be able to predict what would happen when you have a very large number of particles which interact in that particular way. And in the macroscopic scale, in the collective behavior, one finds out many new things which one couldn't have guessed simply by looking at the Hamiltonian of the system. So we'll be talking about basically some such phenomena that we encounter in condensed matter physics. And the basic sort of notion here is that new physical effects arise from the collective behavior of a large number of interacting objects. So new physical effects is very important, that the behavior that you see in the macro scale sometimes could be very strange, given the particular simple Hamiltonian that you have in your system. And this effects arise in the collective behavior of the system. So you have to have a large number of particles and the system as a whole. We look at that behavior, macroscopic behavior of the system. And the interactions is very important. These interactions that we'll see as we go along lead to this emergence of many new interesting and in some sense unexpected phenomena that you see at the macro scale. So there are a couple of sentences in this article that I should read to you, which basically tells you the essence of the kind of phenomena that we want to discuss. The ability to reduce everything to simple fundamental laws does not imply the ability to start from these laws and reconstruct the universe. So the universe is kind of a parable, but the point is, when we are looking at macroscopic objects, we may know the underlying physics in the sense that at the level of microscopic physics, we know how the particles are interacting with each other, what kind of statistics they have, and so on and so forth. But when we look at the system consisting of a very large number of such particles, just by looking at the Hamiltonian, one would not be able to predict what happens at a macro scale. And at a macro scale, one can sort of encounter phenomena which are interesting, which are novel in the sense that they require basically a new description, new kind of description to understand what is going on at that level. So that is what is said here, that at each level of complexity, new properties appear. The understanding requires research that I think is as fundamental as the nature, in its nature, as any other. So he is emphasizing the fact that a lot of effort, of course, has been gone into the study of physics at a very microscopic scale, high energy physics and things like that, which is of course very, very important. But that does not, I mean, understanding physics at that microscopic level does not always tell us what is going to happen when you are looking at a system consisting of 10 to the 23 such particles. And at that level, at that macroscopic level, new phenomena emerge. And those are the phenomena that I'll be calling emergent phenomena. And I'll try to illustrate this by some examples as we go along. So, as I mentioned at the beginning, the kind of phenomena that I will spend a lot of time on as emergent phenomena is this phenomena of phase transitions. And I have chosen this because this phase transition is something that this occurrence of phase transitions and some properties, materials near phase transitions, etc., are studied in undergraduate physics. So I'm sure you are familiar with many phase transitions, but what I want to point out is that the study of these phase transitions brings out new concepts, and a particularly new concept, which is a good example of this emergent phenomena, is this concept of spontaneous symmetry breaking. So this is what I'm going to spend some time on, and we'll see as we go along. So all of you know what phase transitions are all about. It's basically a macroscopic object. One is looking at macroscopic properties like pressure, temperature, density, all those things. And then one is looking at system and changing some parameters, like, one can change the pressure, one can change the temperature, etc., etc. So then there is this two-dimensional plane, y-axis pressure, x-axis temperature. There are lines which separate different phases. What I mean by different phases is that these are the same material, of course, and the material is not changing. But the macroscopic behavior is changing in a very profound way. And so one can distinguish between different phases of the same material. For example, I mean, if a standard phase diagram that you see here is that most of the systems, most of the materials that we're interested in will have different phases. One phase will be a solid phase, typically a crystalline solid phase. One phase will be a liquid. And then high temperatures, low pressures, there will be a gas phase. So all of you know about this, liquid, gas, and solid, three phases of matter. This is a very simple example of phase transition, and there are these lines in this pressure temperature plane, such that if you cross one of these lines, then you go from one phase to another. As you cross this line, let's say fixed pressure, as you're changing temperature, cross this line and you go between liquid and gas. Here you go between solid and liquid, etc., etc. So these are the behaviors that simplest example of phase transitions that all of us know about. There is an interesting point here. This is called the critical point that I'll come to later on. I mean, the behavior that you see here near the critical point is quite different from the behavior that you see away from the critical point. The material that you are most familiar with is, of course, water. And then this is the phase diagram of water, again, temperature, pressure. And you have the solid phase, which is ice, water, and water vapor. And as you change temperature, pressure, then one can go from one of these phases to another of these phases. And here also there is a critical point here, which the line that separates the liquid and the gas phase, that basically ends at this point. Beyond this point, there is no difference between the liquid form of water and the vapor form of water. So something interesting is happening here, which I'll come back to as we go on. So these are the phenomena, because there are many, many other kinds of phase transitions that people have studied. And we are going to study this, discuss many of these phase transitions and try to understand, in some sense, what is going on there. And in particular, this symmetry breaking concept will become very important as we go on. Before that, I mean, this is just some classification of phase transitions. First order phase transition, again, this is something that I'm sure you have seen in some thermodynamics course or something like that. First order phase transition, in which quantities such as the density, entropy, etc., they change discontinuously. As you go from, let's say, across this transition line, you go from liquid to the solid, and these two phases have different densities. So as you cross this line, there is a discontinuous change in the density. Similarly, here also, the water vapor and liquid, they have very different densities. But this is where the importance of this critical point comes into the picture. That as we go along this phase boundary, here, as I said, there will be discontinuous change in the density. The liquid density and the gas density will be very different. As you go along this line, then this difference becomes smaller and smaller. And at this point, the difference goes to zero. So beyond this point, there is no difference between liquid and gas. So the behavior that you see here and the behavior that you see near the critical point are going to be different in the sense that there is a discontinuity in the density and other thermodynamic parameters here, and that discontinuity goes to zero, and you have what is known as a continuous transition at the critical point. This is what I have just mentioned here. First derivative of the free energy, which are volume, entropy, magnetization, etc., are changed discontinuously at this transition. Then transition is called first order. And all these transition lines, solid, liquid, liquid, gas, here also solid, gas, these are first order transitions, except that there is this special point where the discontinuities go to zero, and then these things change continuously across the transition. And these are called continuous phase transitions, or second order phase transitions sometimes, but continuous phase transition is the better way of discussing what is going on, in the sense that things are changing continuously. There is no abrupt jump in the value of the quantity that you are looking at. So these are the two kinds of phase transitions that are there, and we'll be looking at some of those. And just to mention that, behavior near this continuous phase transitions is very interesting and very difficult to work out theoretically. But Ken Wilson received the Nobel Prize for developing a set of methods. It's called the renormalization group methods, which basically tell us about how to treat theoretically the behavior near one of these transitions. So till now, I have been just showing some slides and telling you about some definitions and things like that. I thought it might be interesting for you to look at a few movies. So here is a movie that deals with the liquid to solid transition. It's a first order transition. And one of the characteristics of this first order transition is that it is possible to supercool or superheat in the sense that one can, let's say, take water and you are cooling the water. You can go to a temperature which is lower than the freezing temperature of water, and then the water will still remain in the liquid form. That is the supercooled water. And similarly, you can take solid ice and heat it to a temperature which is higher than the melting temperature, and for a small range of temperatures, it will still remain in the ice form unless you do something drastic to the system. So this is a property of first order transitions where you can have this supercooling or superheating going beyond the phase boundary and still maintaining the original phase of the system. But this is not the when you supercool, the liquid has come to a temperature which is lower than the freezing temperature, so it is not the thermodynamically stable phase. It is a metastable phase, and the system changes from this metastable phase to the stable phase when there is some disturbance. So there is a movie here which I'll show a little bit, which shows this kind of behavior, that you can supercool water, and then if you create some disturbance, then this supercooled water will rapidly go into the solid phase, which is the stable phase at that temperature. So let's see if the movie works. So what one is doing here is that taking a bottle of water and put it in a freezer, and it freezes sometimes, but it doesn't freeze sometimes. It remains in the water form for some time, and then you give it a push, give it a kick, then it freezes completely. So initially, the system was in the supercooled liquid phase, and then after you hit it, then this disturbance basically takes it to the stable phase, which is the solid phase. And then you can see here that the supercooled water, if you pour it, then again the disturbance that we are making will basically transform it to the stable form, which is the ice. So we are looking at, of course, two phases. You can distinguish between the water and the ice, and there is a transition from one to the other. And this is happening in a supercooled water when you disturb it in some way. So this is an experiment that you can do at home, and this is something that tells you about the first order nature of the transition. Then in the next slide, I'm showing this other kind of transition, which is a continuous transition, a liquid gas critical point. And there is no discontinuity, but there are very large fluctuations. So you have here basically a tube where there is liquid at the bottom and gas at the top, and then we'll be heating it and going beyond the critical point where this distinction between the liquid and gas disappear. And then when we cool it, again, there will be separation between the gas and the liquid. But what you'll see is that near this meniscus, where down below that you have the liquid phase and above you have the gas phase, this will exhibit large fluctuations. So this is another simple movie clip that illustrates this behavior. So one is heating this system, and eventually you will see that the surface that separates here below you have liquid, above you have gas. This will disappear. Basically, you are going beyond the critical point, and this is what's happening now. And now there is no surface that separates two phases because the two phases basically become the same. And then you cool it, and eventually it will again come to the two-phase region. But before doing that, in the process of doing that, it will show very large fluctuations. As you can see here, this band that you see, the black band that you see, is the interface, and you can see a lot of fluctuations are taking place there. And eventually, as you go away from the critical point, again these fluctuations die down, and you will have again a sharp interface at a lower temperature. And this basically happens because what I have said here, surface tension between the two phases goes to 0, and the density also becomes same at the critical point. So then this line that separates the two phases, that disappears, but then when it comes back again through the critical point, you can see very large fluctuations associated with this continuous phase transition. Let's see one more such example, which is quite different. I mean, this is something that other things that you have seen in real life, but here you have to be in a lab to see this. And this is this superfluidity transition in liquid helium-4. So the phase diagram is here, temperature, pressure. So you have the normal liquid, you have a solid, you have a gas, etc. as before. But the new phase comes here when you have very low temperatures, below 2 degrees, and relatively high pressures. And there, system goes into what is known as a superfluid, where the fluid basically has very strange properties, in the sense, many strange properties. One of them, the easiest thing to look at, is basically that it can flow without any dissipation. It can flow without any friction or any viscosity. So let's see a simple demonstration of this. One is cooling liquid helium. And you see this is lots of boiling, etc. going on. And then as you go into the superfluid phase, everything becomes still. And there is one more clip here that shows that superfluid can flow without any friction. Superfluid can flow without friction, so it can go through very small pores. And as you can see here, when it becomes superfluid, it can actually go through. So these are examples of phase transitions, and these are, of course, as I said, phenomena in which the property of the system changes very drastically. It can change discontinuously in first-order phase transitions. It can change continuously in other kind of phase transitions, continuous phase transitions. And there are many, many such phase transitions that we'll be talking about as I go along. My contention is that all of these phase transitions, the majority of these phase transitions, are examples of what I call emergent behavior, which one couldn't predict very easily just by looking at the microscopic interactions and things like that. So again, there are many other examples of phase transitions. I'll be talking about magnetic phase transitions. I'll be talking about superconducting phase transitions, then liquid crystal, etc., etc. So again, just to give you an idea that there are many, many different phase transitions that one is concerned with in the study of materials. The basic aspect of phase transition that I want to concentrate on, because that is what actually can be thought of as an emergent property, is this spontaneous symmetry breaking. So we have just discussed phase transitions, and majority of the phase transitions, not always, correspond to a change in the symmetry of the thermodynamic state of the system. So usually, let's say, you're decreasing temperature. So high temperature phase is usually, it has a lot of symmetry. As you go down in temperature and cross the phase boundary, go to the low temperature phase, then typically what happens is that some of the symmetry that you had, the thermodynamic state at high temperatures, is no longer there. It's broken at the phase transition. So this is the aspect that is very intriguing, and that's what I'm going to talk about in the next 15 minutes. So this is what I say here. The low temperature phase usually breaks one of the symmetries of the underlying Hamiltonian. And what I mean by that, I'll give many examples. But the simplest example that you're familiar with is basically going from, let's say, liquid to a crystalline solid. Liquid, the particles are not arranged in a regular fashion, and these particles are moving all the time. So if we look at a liquid, and if you could actually look at it very microscopically, you will see that the atoms or molecules which constitute the liquid, they're actually moving with fairly high velocity, and they undergo collisions and so on and so forth. They change velocities and this and that. So that is the microscopic property. In the macroscopic sense, what you see is that the liquid is uniform. that if I look at a particular point inside the liquid and look at some other point inside the liquid, there is nothing that distinguishes these 2 points. If we look at the average density, for example, average density is the same at every point in a liquid except near the boundaries. In that sense, the high temperature liquid phase is transitionally invariant. Whereas if I now cool it below the crystallization point, then you get this crystal. And here, the transitional symmetry is broken. In the sense, in the crystal, the particles are not going over the whole system. They are basically localized at lattice points of a crystal, which make a regular structure. And the particles vibrate about this lattice points, but they don't go from one lattice point to another over reasonable time scales. So what you have here is that a structure that looks, let's say, something like this. It's hexagonal triangular lattice. And the points where the particles are sitting, you have large densities at those points, local densities at those points. And those points basically are different in some sense from the points where a particle is not sitting. So if I look at a point in between, let's say interstitial point, which is in between 3 particles, no particle is there, then that point is different from a point where a particle is sitting. Whereas in the liquid, every point is equivalent in the sense that, this picture, one can say that this, where a particle is sitting and where the particle is not sitting, these 2 might be different, but this particle will not sit here forever. It will travel around. And if I look at the thermodynamic state of the system, then that state is transitionally invariant. Whereas if I look at it here, even if you average over time, the points where the particles are located, there will be large density at those points. And when the points where the particles are not located, they will have low density. So this state basically breaks the continuous transitional symmetry that you have in the liquid phase. And as you go from here to there, there is this spontaneous breaking of the symmetry. So this is the main phenomenon, and I'll sort of elaborate that a little bit as in the next few slides. So, this is something, just the concept of symmetry that I'm invoking here that needs to be understood. So this is something that all of you know, that there are transformations that keep a particular object invariant, and those transformations are the symmetry transformations. So if I look at a triangle like that, there are many symmetries. For example, if I look at the central point and then rotate the triangle about an axis which is perpendicular to this plane by an amount which is 120 degrees or 240 degrees, what happens is that this vertex will go there, this will go there, etc., and we get back the original thing. So that is a symmetry operation. That's something that I have done, but that doesn't change this triangle. You get back. I don't distinguish between the 3 corners. So as long as these 3 corners are equivalent to each other, when I do this rotation, one corner and that corner gets interchanged, and that gives me back the original object in the original position. So that's a symmetry operation. One can also, for example, draw a perpendicular from this vertex down to this this base, and that one can reflect, make a reflection about that line, and then this vertex will go to that vertex, and these 2 will be interchanged. Nothing will change. So these are typical examples of symmetry operations. But these are discrete operations that here we're changing by 120 degrees or 240 degrees, and you're doing a reflection, which is by definition is a discrete process, a discrete transformation. So there are these symmetries which then tell us about transformations that keep the object invariant. You can go to a more symmetric situation, a circle, and then again, you look at the center of the circle and take an axis which is normal to the plane and make a rotation of any angle about that axis. Circle will keep looking the same. Nothing will change. So here again, these are the symmetry operations, but one is talking about continuous symmetry in the sense that rotation by any angle will basically leave the circle invariant. So this is sort of the everyday concept of symmetry, that there are objects such that under certain operations, the object remains invariant, and those are the symmetry operations. What I'll be talking about is a little more complicated. We'll be talking about the symmetry of the Hamiltonian. So Hamiltonian is the energy function that describes a system that you are interested in. System of particles will have basically kinetic energy term p squared over 2m. The term that I'm interested in more is this interaction term. which depends on the distance between. So Ri and Rj are the positions of ith particle and jth particle, and this V is some function. I'm not specifying what that function is. I've given you some examples at the beginning. So the potential is a function of the distance between the two particles. And as you all know, the distance is not affected if I move both of the particles by the same amount. So I have a uniform translation. Ri goes to Ri plus some constant value for all I, which will keep this distance invariant. So the Hamiltonian, in this case, is invariant under an uniform translation. This is what I was talking about when we were talking about liquid to gas. The Hamiltonian of such a system is invariant under a uniform translation, and the liquid phase, that invariance remains. The liquid phase also is invariant under a translation, because on the average, every point in the liquid is equivalent to every other point in the liquid. We'll be talking about various magnetic systems, where I've written down a Hamiltonian, which is very familiar, or which is very common in studies of magnetic systems, where you have some interaction constants, Jij, and then Si is the spin or magnetic moment at site I, Sj is the magnetic moment at site J, and you have a dot product between these two, and then you have sum over pairs of such terms. And dot product, as you all know, invariant under uniform rotation. If I rotate both Si and Sj by the same amount, then this dot product doesn't change. So again, the symmetry of the Hamiltonian that is important here is invariant under uniform rotation of the spin vectors. So this is these are things that are important. That system that we are interested in, it will have typically a Hamiltonian. The Hamiltonian will have some symmetries depending on what kind of systems you're looking at. A particle system, typically, if you have just pair interactions, no external potential, then you have Hamiltonian invariance under uniform translation. If you have some kind of exchange interaction in Heisenberg model without any external magnetic field, again, you have a symmetry, global symmetry, which is symmetry under uniform rotation of the spin vectors. Question is that the thing that we'll be seeing shortly is that this kind of symmetry that you have is typically also there in the high temperature phase, but this symmetry may be spontaneously broken as you go to across the phase boundary, as you go to an ordered phase, in which we'll see that the ordered phase itself basically breaks some symmetry that may be present in the Hamiltonian. So then one talks about the symmetry of the thermodynamic state. That is what we are interested in. We are interested in various thermodynamic states of the system, maybe above the transition, below the transition, and then try to find out whether those states preserve the symmetry that you have in the underlying Hamiltonian or not. So there, one has to have, to understand what is going on here, one has to have basically some idea about how one is going to describe a thermodynamic state, because again, you are looking at a system consisting of a very large number of particles, so you cannot really know where exactly each particle is located, what velocity the particles are, and so on and so forth. So one has to have something like a statistical description, which is the statistical mechanics description of macroscopic systems. So there, a thermodynamic state corresponds to a collection. Ensemble basically means a collection of microscopic states. Each microscopic state comes with a certain probability. So the ensemble is specified by these probabilities. N is a particular state of the system, microscopic state of the system, and P then tells us about the probability of occurrence of the microscopic state in the ensemble. So thermodynamic state corresponds to an ensemble of microscopic states. System is going through many different microscopic states as it is evolving in time, and we don't know, or we don't want to know, the specific microscopic state system is going through. We are interested more in the macroscopic behavior, and to understand that, one has to specify this quantity, which is telling us about the probability with which a microscopic state appears in the ensemble, which basically describes the time evolution of the system. System goes, as it evolves in time, it goes through many, very large number of microscopic states. So we want to know what is the probability that the system will be in a particular microscopic state in this ensemble during its time evolution. And once we know this Pn, then from that we can construct various thermodynamic quantities. We can calculate that various thermodynamic quantities. So, and different ensembles will have different forms for this P sub L. The typical one is what is known as the canonical ensemble. And here it is important to note this particular form for these probabilities, that we are looking at a particular state N, which has an energy which depends on which state, microscopic state you are looking at. So the probability of that microscopic state in the ensemble is given by the exponential of that energy divided by kBt. This is called the Boltzmann factor. Kb is the Boltzmann constant. And so a particular state, a microscopic state with energy En, will occur in the ensemble with a probability which is the exponential of minus energy divided by this thermal energy, kBt. And Z is what is known as partition function, which basically is a normalization. That sum of all n of P of n has to be equal to 1. And so this Z is basically a sum over all n of this quantity that you have in the numerator. And if you know these probabilities, then you can calculate any thermodynamic average. Any quantity observable O will be basically the sum over all such states, the value of that observable in a microscopic state n multiplied by the probability of that microscopic state n, and then summed over all such microscopic states. So this is statistical mechanics in 2 minutes. So what one is talking about here is this description of a thermodynamic state in terms of the microstates that the system visits during the time evolution when the system is that thermodynamic state. And these microstates appear with certain probabilities, and these probabilities are depending on which ensemble you're talking about, fixed temperature or fixed energy or fixed pressure and things like that. Here we are talking about a fixed temperature ensemble. The probability with which a particular microstate appears is given by these Boltzmann factors. So now this is where the crucial question is. We have talked about the Hamiltonian and its symmetry. Hamiltonian remains invariant under certain symmetries. Here the symmetry is the uniform translation. So if I take a state n and then transform it through one of these transformations, the energy of that state will be the same as the energy of the previous state. Here, if I take a microscopic state where the particles are located at certain positions, and then if I change the locations by the fixed amount, same amount for all the particles, then again the energy will remain invariant. So then going back to this energy of a particular state doesn't change when that state is changed by operation, which is a symmetry operation of the underlying Hamiltonian. So there are many such states which are related to each other by a symmetry operation of the Hamiltonian, and they will all have the same energy. So according to this formula, they should also have the same P, same probability in the ensemble. So this is what one expects from the microscopics, that you have a Hamiltonian, which is some symmetry. You take a microscopic state of the system and then change that state by a symmetry operation. Then the energy of that state is going to be the same as the energy of the previous state. And according to this Boltzmann formula, then these two states should occur with the same probability in the ensemble. And what we'll see shortly is that when a phase transition occurs, and if the phase transition is such that the symmetry is broken at the phase transition, then these probabilities will no longer be the same for these two states which are related to each other by a symmetry operation. So this is the notion of spontaneously broken symmetry, in the sense that here there is nothing in the Hamiltonian that is changing. Above the phase transition, below the phase transition is the same Hamiltonian. But the Hamiltonian has some symmetry, so there are a particular state of the Hamiltonian. If you apply the symmetry operation to that particular state, then it will not change the image. And then naively one would expect that these two states will have the same probability. But this is what doesn't happen at a phase transition. When the symmetry is broken, then one finds that these probabilities with which the different states occur, although they have the same energy, they do not have the same probability. So this is the emergent phenomenon. This you couldn't have predicted simply by looking at the Hamiltonian of the system. That's a microscopic description. Hamiltonian has this symmetry. So you'd expect that the states related to each other by symmetry, of course, they will have the same energy, that nothing much you can do about it. The question is, in the thermodynamics of the system, whether all these states will occur with the same probability or not. And my claim is that at a phase transition, this does not happen. That the probabilities of two different states, which are related to each other by symmetry, and therefore they have the same energy, they will not be the same in the ordered phase of the system. So this is what I'd like to illustrate by giving a few examples. So we are talking about this system of particles. And there, to make things quantitative, I basically define this quantity, which is the average local density, which basically counts the number of particles that are near this point R, and then averages over all the microscopic states system goes through. And as I said, in the liquid phase, this quantity is a constant, and Hamiltonian of the system, which has this potential energy, which is invariant under a uniform translation. So that basically means that this is the symmetry of the Hamiltonian, and the density also is the same at every point. So that is also invariant under the same transformation. So the symmetry is preserved. Original Hamiltonian has symmetry under the uniform translation, and the liquid state also, when you look at the average density, since it is the same at every point, it is also invariant under the same uniform translation. But in the crystalline phase, this density is going to be peaked at certain points, lattice points. And then if I choose this R0 to be a lattice vector, then again it will be invariant, because this will go there, etc. Lattice vector is basically a vector that connects two lattice points. So if I R0 I take to be a lattice vector, then this will go there, etc., and the state also will be invariant. But if we take any other displacement vector, which is not a lattice vector, then this will go, let's say, somewhat to the midpoint, this will go to the midpoint, etc., and that state is not equivalent to the original state. So this is the statement: periodic solid is invariant under translation by lattice vectors, but not under any arbitrary translation. Whereas the Hamiltonian is invariant under every arbitrary translation. And the liquid phase also is invariant under every arbitrary translation. So we are looking at a situation where the high temperature phase is the same symmetry as that of the Hamiltonian, but the low temperature phase breaks that symmetry. It still has some symmetry. It is a symmetry under translation by lattice vectors, but it is not symmetric under translation by any arbitrary vector R0. So this is the spontaneous symmetry breaking that we are talking about. And there are many other examples which we'll come to as we go along. So let me just skip this because I think I'm nearing the end. So can you tell me how many minutes I have before this lecture has to be ended?
You can take your time, sir. At the end, we have a couple of questions.
So maybe 10 minutes, I'll finish this one?
Yes, sure. You can take your time.
Okay, so liquid crystal transition and magnetic transition I'll talk about later on. So let me just skip that. But I introduce a model in which it is very easy to see this concept of broken symmetry. This is a model for magnetic transitions, liquid gas transition, binary alloy, many physical systems that are described by this simple model, which is called the Ising model, which is studied a great deal in statistical mechanics. In some cases, one can solve the problem exactly and so on and so forth. So this is a very popular model. So what I'm writing down here is again the Hamiltonian. Hamiltonian involves pairwise interactions, pair I and J, and these are the variables. These are the variables of the problem. These are called Ising spins. Each variable can take the values plus or minus 1. So the sigma I, sigma j, this product can have two values. If both of them have the same spin, then it will be plus 1, and if both of them have, if the two have different spins, then this sigma I, sigma j is going to be minus 1. And in general, one can also put in something like a magnetic field, which says that if H is positive, then the energy, there's a negative sign here, energy of sigma I equals plus 1 is going to be less than the energy of sigma I minus 1. But we'll generally not look at this term. This term will be set equal to 0. So only the interaction term. And we'll say that this Jij is the simplest model, is some positive number if I and j are nearest neighbors and equal to 0 otherwise. So the spins are sitting on a lattice, just like here, and the nearest neighbor spins interact with each other with a coupling constant, which is positive and which is some value. Doesn't matter what this value is. The point is that if j is positive, then the spins want to be of the same sign. So if j is positive and then sigma I, sigma j are both plus 1 or they are both minus 1, then the energy is negative. And since j is positive, if one of them is plus 1, the other one is minus 1, then this gives me a minus, and that goes with that minus to give me a positive energy. So a pair of spins, if they are aligned in the same direction, then you get basically the energy is lowered, and if they're anti-parallel to each other, then the energy is higher. So if I want to, for example, find the ground state of the system, very easy to see that all the spins will be pointing in the same direction in the lowest energy state, in the ground state of the system. That is what is called ferromagnetic ordering. And so, I mean, this is the ferromagnetic state where all the spins are pointing in the same direction. So for each pair, you get a minus J, and that is that's the way the energy is minimized in the ground state of the system. But if you have this disordered state, which is called a paramagnetic state, then some spins will be pointing up, some spins will be pointing down, and then in some cases you will get a minus J for a bond, you'll get plus J for a bond. So it will be higher energy state. So this is the very simple model. And what we'll be interested in is this ordering, in which the average value of a spin is going to be non-zero. We are looking at H equals 0. So forget about this H term, but just this term. And there we are looking for states in which the average value of a particular spin is going to be non-zero. And here you can see this M is going to be equal to 0 in the disordered phase, which is called the paramagnetic phase. And what happens is in this model is that as you are in decreasing temperature, then this magnetization, which is the average value of a spin, and this is what is happening here, the temperature is decreased, and high temperatures, this average value is equal to 0, so you're in the paramagnetic state. And then as you go below a critical temperature, then this magnetization becomes non-zero, and you go into the ferromagnetic state. This is a two-dimensionalizing model, one of the sort of celebrated models, which can be solved exactly. So the results that I'm plotting here are actually exact solutions of this model, which is due to Onsager, again, for which he got a Nobel Prize many years ago. So this is the phase transition that we're talking about. We are talking about a transition from a paramagnetic state in which the typical states will have some spins pointing up, some spins pointing down, some sigma is positive, some sigma is negative. And then as you go lower the temperature, eventually you go to a ferromagnetic state where majority of the spins will be pointing in the same direction. And so this average value of the spin will be non-zero. But this is an example, very simple example of this spontaneous breaking of symmetry. So this is what is explained here, that the Hamiltonian is this. This is what we wrote down in the previous slide, and H is equal to 0. So what is the symmetry of the Hamiltonian? If I change the sign of sigma I for all I, then change of sign basically brings in a change of sign for sigma I, same change of sign for sigma j, which doesn't change anything. So the Hamiltonian is invariant under sigma I going to minus sigma I for all I. That is very clear, right? I mean, let's say both of them are +1, then you'll get +1 here. Both of them are -1, and again, then you get +1 there. So the energy doesn't change when you change the signs of all the spins. So E sigma I, collection of sigma I, is the same as E is a collection of minus sigma I. This is the symmetry of the Hamiltonian. But if you're in the ordered phase, then you see a non-zero magnetization, which basically means that the probability of this state, microscopic state, is no longer the same as the probability of this microscopic state, which is obtained from here to there by changing the sign of all the spins. So this is illustrated here. Let's say here you're looking at a state which has all the spins +1. Here's a state where all the spins are -1. Energy of this state, the same as energy of that state. And that is given by the symmetry of the Hamiltonian, that if I change the sign of all the spins, energy doesn't change. So these two states have exactly the same energy. So according to my canonical ensemble, energy of this all the sigma pointing in some direction and the energy of all the spins pointing in opposite direction, these two are the same. But we get a non-zero magnetization. These two states have the same energy, but the state with down spins does not appear in the ensemble for the ordered state when M is equal to 0. So when, as you go to temperature below this transition point, then the order parameter will be non-zero, which basically means preferentially we'll see this. Let's say if M is positive, preferentially we'll see this. If you see both this and that with equal probability, then M cannot be non-zero, because this by definition, this state and that state, all the spins are reversed in going from this state to that state. So if these two states in the ensemble, they occur with the same probability, then they will just cancel each other for each microscopic state. And then you cannot have a state with a non-zero magnetization. So basically, the fact that you do see a non-zero magnetization at temperatures less than Tc is basically a statement that says that this up-down symmetry is broken, spontaneously broken in the ferromagnetic phase. The paramagnetic phase, m is equal to 0. So that state has the same symmetry as that of the Hamiltonian. The symmetry is where you change the signs of all the spins. So there the symmetry is not broken. But as I go to a temperature which is lower than the critical temperature, then you have a finite magnetization. M can be positive or negative. It doesn't have to be always positive. But if it is positive, then this state is seen with a much higher probability compared with that state. And if the M is negative, then this state is seen, the negative state is seen with a higher probability than that state. Although the Hamiltonian is invariant under this symmetry operation, which says that this state and that state, they have the same energy. So although these two states have the same energy, they do not appear with the same probability in the ensemble for temperatures lower than the transition temperature. So this is basically the spontaneous breaking of symmetry. There is nothing externally that is being done to the system. One is just reducing the temperature, and at high temperatures is in the paramagnetic state where up and down states, plus m and minus m states, they have the same probability, so they average out to 0. There is no net magnetization. Below this transition temperature, one of them, one class of states, either with positive magnetization or with negative magnetization, they have more probability as compared to the spin reversed state, and this symmetry, the symmetry that one has in the Hamiltonian and also in the high temperature phase is spontaneously broken. As a result, one picks up a non-zero value of the magnetization. So this is basically something that one couldn't predict just by looking at the Hamiltonian. The Hamiltonian is symmetric. So it says that state with plus m and state with minus m must they have the same energy. That is always true. But the question is whether these two states occur with the same probability at all temperatures, and temperatures lower than the critical temperature, this does not happen like that. And this symmetry is spontaneously broken. And this is an emergent phenomenon that happens because you have a very large number of particles which are interacting with each other. And just the last transparency I showed today, which basically tells you why this happens. And this is where the thermodynamic limit, or the limit of infinite system size, appears. So let me just go through this in a few minutes. So here again, I'm showing it in color. This is basically a square, and there are, you may not be able to see the individual points, but there are basically spins, decising spins sitting at individual points in a lattice. And when the spin is pointing up, where the sigma is +1, I draw it with red. When it is -1, I draw it with green. So in general, I mean, a particular microscopic state will correspond to some red points and some green points. And if you want to have a state with finite magnetization, then it will be mostly, if you want a magnetization which is positive, then it will be mostly red. If you want a state with where the magnetization is negative, you want mostly green. Now let's say the system has got into a state which is all red, let's say mostly red. Then there will be also a state with equal energy, which will be mostly green, which is obtained by flipping all the spins that you have in the system. But the question is, how does the system goes from this mostly red state to the mostly green state? And to go through that, there has to be in-between state, which has partly red, partly green. I mean, if for example, imagine initially the whole thing was red, and then I'm trying to find out how the system actually goes from that state to a state which is everything is green. Then to go from here to there must be a state which is in between, which has some red and some green. The point is the energy associated with this state, the excess energy that is associated with creating this separation, which is called a domain wall. System has to go through a domain wall in order to explore ordered states with positive and negative. If one wants to go from all red to all green or vice versa, then the intermediate states must have this kind of a domain wall, which is separating a red region from a green region. And it is very easy to see that the energy of this domain wall, excess energy of this domain wall, is 2 times the coupling constant times the length. Length is how many spins are there across this dimension of the system. So if there are L spins along this domain wall, for each such spin, you have an excess energy of 2 times J, because initially when they're in the same sign, then you have minus J, and when the spins are different sign, then you have plus J, so the difference is 2J, and if there are L such sites, then the total energy will be 2Lj. Now, in the thermodynamic limit, if you have infinite number of particles, when L goes to infinity, this energy actually goes to infinity. So the intermediate state has infinitely high energy, and the system can never reach that intermediate state where it is partly red and partly green. So if it initially gets into a state which is mostly red, then it will stay there. It will not go to the state where it is mostly green, because in going from the initial state to that state, it has to overcome energy barrier. Energy barrier is coming because there has to be a domain wall which separates partly red, partly green, partly red regions from the partly green regions, and the energy associated with that domain wall will diverge in the thermodynamic limit. So the Boltzmann factor corresponding to that particular state is essentially 0. So once the system goes into a predominantly red part, it remains there. If it goes into a predominantly green part, again it goes there and stays there. These two things don't get mixed. So that is what gives rise to a non-zero value of the magnetization. Although the energy of a particular microstate and the energy of the microstate obtained by reversing all the spins in the first microstate, these two are 0. So according to the Boltzmann statistical mechanics, these two states should appear with the same probability. But if a system has a very large number of spins, then below a certain temperature, these two states do not appear with the same probability in the ensemble. And one has basically a spontaneous breaking of the symmetry, and one basically has non-zero value of the magnetization. So this is what I call an emergent property, that just by looking at the Hamiltonian, since it's symmetric under the reversal of all the spins, you would conclude that the magnetization should always be equal to 0. But in reality, and this can be done exactly as Onsager did for the two-dimensional system. For other higher dimensions, you cannot solve the problem exactly, but one can do a very good job of thermodynamics, and one finds that there will be a critical temperature below which this symmetry that one had at the original Hamiltonian, that symmetry will be spontaneously broken, and one would pick up either a positive or a negative magnetization. And this symmetry that says that two states which are linked to each other by reversal of all the spins have the same energy does not translate into these two states having the same probability in the ensemble that one is looking at. And as a result, that symmetry is spontaneously broken. And this, I would imagine you will accept as an example of an emergent phenomenon, because just by looking at the microscopic Hamiltonian, we couldn't have predicted that this is going to happen, but this is what happens at the macroscopic scale, because you have a large number of interacting degrees of freedom. So I think this is a reasonable place to stop. Is that okay? Hello?
Yes, sir. Yes, sir. So moving on to the questions, we have a couple of questions. The first one is, what can we say about thermal and electrical conductivity of superfluids? Specifically, the example taken, that is the superfluid helium that you've taken. What can we say about thermal and electrical conductivity about it? Okay.
Oh, the electrical conductivity of superfluid helium, is that the question?
Yes, sir.
Electrical conductivity is nothing special, because it still will be an insulator, because you see the particles which constitute the fluid, they are helium-4 atoms, and the atom doesn't carry any charge. So even if I can create a motion in the system such that this motion persists in time without any friction, without any viscosity, but that motion doesn't carry any current, because the particles that are moving, they are neutral. So basically, although in a superfluid state, the particles can move very smoothly, in the sense that they're not affected by friction arising from viscosity. Superfluid has 0 viscosity, but this motion does not carry any current. So the electrical current, electrical resistivity doesn't show any special behavior in the superfluid phase. The behavior is different in a superconductor, because there the quantities that are equivalent to, so to speak, this helium atoms Those are pairs of electrons called Cooper pairs. This is something that I'll come to in one of the lectures later on. And so these Cooper pairs can move without friction. And as a result, I mean, when they move without friction, they also can carry a current because they're all charged particles. And this is what makes the resistivity, electrical resistivity of a superconductor zero in the superconducting state, because there are charged particles which are moving without any friction. Whereas in a superfluid like helium-4, since the constituting particles are not carrying charge, one doesn't see much of an effect on the electrical conductivity. Is that clear?
Yes, sir. The question also asked about the thermal conductivity.
Thermal conductivity is a somewhat more complicated situation. There, actually, the particles, you see, okay, the question is basically what gives rise to thermal conductivity. It's not the particles themselves that are moving. So if you look at a piece of metal, and if I look at thermal conductivity, then what happens is that the high temperature at one end, which causes the atoms or molecules in the crystal to vibrate with a higher amplitude, and then that basically transfers heat from one end to another. Mostly it comes from phonons or these lattice vibrations. In a liquid, of course, these lattice vibrations are not there, but in a superconductor, for example, thermal conductivity is going to be very small. Because again, it's the property of the electrons that are there, which causes the thermal conductivity to be very low. In liquid helium, thermal conductivity also I would expect to be low, but this is something that I have to check myself, and I have not looked at it very recently. So thermal conductivity of superfluid state I expect to be low, but I don't know, because there the particles themselves can move. And the heat current may be carried by the particles themselves. And if they can move without any friction, then that would lead to a higher thermal conductivity. But whether that actually happens or not, I have to check. Because there are hydrodynamic effects and things like that occur because you're talking about a liquid. In a superconductor, thermal conductivity is low. Electrical conductivity is high.
The next question is the system governed by a new probability distribution after the critical point is reached rather than Boltzmann distribution?
Can you repeat that? I couldn't hear that very well.
Is the system governed by a new probability distribution after the critical point is reached rather than Boltzmann distribution?
So the Boltzmann distribution does not work below the transition point. So, I mean, you see, this is what I'm trying to explain, that the Boltzmann distribution will give you the same probability for, let's say, predominantly up state and predominantly down state. Because if you go from this predominantly up state to the predominantly down state by just stripping all the spins at the same time, that doesn't change the energy. The Boltzmann probability depends on the energy. So if these two states, since they have the same energy, according to Boltzmann distribution, they should have the same probability. But the system has a finite magnetization that basically says that these two states don't have the same probability. Let's say magnetization is positive, basically says that the state that is predominantly upspin has a higher probability than the state that is predominantly downspin in a particular thermodynamic state. So in that thermodynamic state, the Boltzmann distribution does not work. But then, there would be, if I do the experiment again, some other time I'll get a predominantly down state. So both these two, the predominantly up state and the predominantly down state, they will occur with equal probability. But in one experiment, you will see only one of these. That in one experiment, as you pull it down, then magnetization can be positive or negative. That you can't predict before you actually do the experiment. But once the experiment is done, then the system will be below this TC, below the critical temperature. System will be in one of these states, plus M or minus M. And if it is in the plus M, then the probability of the minus M state, of course, is 0, basically. So although these two states have the same energy, they don't have the same probability. So the Boltzmann distribution per se will not work below this order disorder transition. But it is the fact that these two states have the same energy is reflected in the fact that if you do the experiment 100 times, then on the average, 50 times you will get a plus m and 50 times you will get minus m, because there is no, in some sense, preference for plus m or minus m in the Hamiltonian of the system. But in a particular experiment, you will get either plus m or minus m. So the state that you get below this TC breaks that up-down symmetry, and in that state, naive Boltzmann distribution will not work.
We have a question.
Yeah.
Argument about TC.
I'm sorry?
What happens to parallel argument about TC?
Above TC. So above TC, you are not, typical state will not have this structure. So below TC, you are supposed to have a magnetization. So it's going to be a predominantly red region and a predominantly green region. One positive magnetization, one negative magnetization. But above TC, because the spins are flicking, because of the thermal energy is high, you will get, if I just want to draw a state which is above TC in this particular scheme, then you will get a mixture of plus and minus. So you will get, you may get pockets of plus, which are surrounded by minus, pockets of red surrounded by green, or the other way around. And this kind of distribution of red and green, or plus or minus spin, will be present in all parts of the system. The reason that happens is that, you can see that a state which has basically, let's say, equal number of plus and equal number of minus, this state will have a high entropy, because there are many, many different ways in which you can construct a state which has half of them plus one and half of them minus one. Whereas if I want to have all of them plus one, then there is, of course, one such state. All of them minus one, there is just one such state, such as things like that. So at high temperatures, where the entropy plays an important role, typically you will have the microstates in which the plus and minus will be equal number, and they will be distributed uniformly, more or less, throughout the system. And there is no such domain wall concept. Domain wall concept is there only when you are separating a predominantly red, a predominantly plus region, and a predominantly down region. Only then you can basically say that to separate that, plus m and minus m, you have to create something, and there the energy will be large associated with this domain wall if the domain wall is long. But you can imagine where both these sides were a mixture of red and green, then such a domain wall energy will not be extensive in the size of the system. So the domain wall energy per unit length, that goes to zero in the disordered phase, where you have basically a mixture of both red and green. Whereas when you have a finite magnetization, then you can talk about, on one side you have plus m, other side you have minus m, and then the domain wall energy will come into the picture.
The next question is, how is superposition achieved?
I'm sorry, but we cannot hear that very well.
How is supercooled state achieved?
How is superfluid state achieved?
Supercooled state, yes, sir.
Oh, supercooled state. So, and supercooling and superheating, these are possible only when you have this first order transition, where there is a discontinuity. And another characteristic of such first order transitions, maybe in the next lecture I'll have some time to sort of talk about that, is that near the transition, both the ordered and the disordered phase are local minima. So what is happening here is that, so local minima of what? So there's some kind of a free energy. If you know thermodynamics, then you know different kinds of free energies. So this free energy have different minima. And the thermodynamic state corresponds to a minimum of that free energy. Now, what happens in first order phase transitions is that there is one minimum that corresponds to the ordered state, another minimum that corresponds to the disordered state. So if you're talking about the water freezing, then there will be one minimum that corresponds to the liquid phase, the water. The other minimum corresponds to the solid phase, which is the ice. And both of these minima can exist simultaneously over a temperature range, which is near the temperature where the transition takes place. So let's say you are cooling the system. So system is in the minimum, which corresponds to the water, liquid phase. And as you go to a temperature which is lower than the transition temperature, that minimum still remains as a local minimum. What happens is the minimum corresponds to the crystal phase that has a lower free energy than the one that you had for the liquid phase. So they just both these minima exist, but the values of the free energies of these two minima, they become equal at the transition point. And as you go either way to higher temperature or lower temperature, then one minimum becomes deeper than the other minimum. So what is happening here is that if you're just crossing the phase boundary, then at that temperature, both the liquid state corresponds to a minimum and the solid state also corresponds to a minimum, although the solid minimum is lower than the liquid minimum. So basically, the system can remain in the liquid minimum for a while. And if you disturb it, then it can go over appropriate barriers and then go to the more stable minimum. This is what happens when you have this. We saw that if you have the water, supercooled water, if you disturb it by giving it a hitting the bottle or something like that, then it goes from there, from the original liquid minimum, which is still a minimum, but it has higher free energy, to the minimum, which has the lower free energy, which is the crystal minimum. And that is the nucleation of the solid that you saw, that some disturbance basically takes the system from the metastable liquid state to the more stable solid state. And this happens only in first order phase transitions, where both these minima can survive as local minima at temperatures which are close to the transition temperature. In a continuous transition, that doesn't happen. So, I mean, this is something that perhaps I can explain in the next lecture, where this distinction between the first order and continuous transitions is important. That in the first order case, you can have this metastability or this super cooling or superheating, whereas in a continuous phase transition, you don't have that phenomenon taking place.
The next question is, can we say we can't use Boltzmann distribution as phase transitions aren't equilibrium phenomena?
So, as I said, the Boltzmann distribution is perfectly all right if we are in the disordered phase. In the paramagnetic phase, the phase has the same symmetry as that of the Hamiltonian. So there are two states which are related to each other by symmetry, and therefore they have the same energy. They occur with the same probability. And so Boltzmann distribution, there is no problem with it. Only as you go below the transition point, where you have a positive or negative magnetization, then you are a little bit of trouble, because although a plus m state and its counterpart, a minus m state, according to Boltzmann distribution, they should have the same probability, but they don't occur with the same probability in the ensemble that corresponds to the physical system. So the Boltzmann distribution as such will not work at temperatures lower than the critical temperature. But there are mathematical ways of taking care of that. So one popular way is to apply a very small magnetic field. So if I go back to the Hamiltonian here, you see that there is a, you can still see it, right? Slides are still visible, right? Hello?
Yes, so they are.
Yeah. So this H term gives you a negative value when sigma is +1 and gives you a positive value when sigma is -1. So this prefers one to the other. So a positive H will give you a higher probability of positive magnetization, and negative H will give you a higher probability to negative magnetization. So if you have this H non-zero, then the Hamiltonian doesn't have any symmetry again, and everything is all right. There is no phase transition, because this already prefers any non-zero value of H will give you a non-zero magnetization, because it prefers one class of states over the other class of states. So the phase transition can occur only when this H is equal to 0. But what one can do mathematically is to take the H going to 0 limit, and the other limit that one has to take is the thermodynamic limit, n going to infinity limit. So the order of these two limits is not the same below Tc. So high Tc, there is no problem. Temperature higher than Tc, these two limits are interchangeable. But as you go to temperature which is lower than Tc, these two limits are not interchangeable, in the sense that, as we had just found out, in the infinite system, one cannot go from the positive magnetization to the negative magnetization. So mathematically, what one can do is that one can first take the n going to infinity limit with h in it, and then let h go to 0. So then, even with Boltzmann statistics, you will pick up basically the fact that in the large n limit, one would have either plus m or minus m. So mathematically, it is possible to actually do this trick that you put in a magnetic field, and then you let that magnetic field go to 0, take that limit, but you take that limit after the thermodynamic limit has been taken, and then the Boltzmann distribution still works at temperatures lower than the critical temperature. But this is something that is a mathematical trick that allows one to use the Boltzmann distribution, even in the case where there is a spontaneous symmetry breaking. But in physically, there is there is nothing that corresponds to this. I cannot take the n going to infinity limit or the h going to 0 limit. The h going to 0 limit, perhaps one can do in experiments, that one apply a magnetic field and slowly change the magnetic field and it eventually to go to 0. That will pick up a particular value of m. If I apply the magnetic field in the positive direction and then slowly reduce that magnetic field to 0, then below Tc, system will always be in the positive magnetization state. Where if there's no magnetic field, then it can be in the positive or negative magnetization state with equal probability. So when it depends, I mean, what you mean by the applicability of the Boltzmann distribution. You can make it work by doing this mathematical trick of taking the limits in a proper order. But in reality, when there is no magnetic field in the experiment, then again, the system will go to a plus m or minus m state at temperatures lower than the critical temperature. And then, obviously, Boltzmann distribution does not work, because these two states should have the same probability according to the Boltzmann distribution.
We've got a final question. Over what scale are the averages taken for defining these densities? Over what scale are the averages taken for defining these densities?
For defining the densities, you mean? Or?
Yes, sir, density.
So now we are talking about the liquid or particle system, and then how the local density is being defined.
Yes, sir.
Yeah. So, I mean, typically what this is something called coarse graining, where, if you look at a particular snapshot, you will see that the particles are basically located at certain points. And there, the density will be basically a set of delta functions for that particular microscopic state. But when you do the average over the state, system, as I said, goes through many different microscopic states as the system evolves in time. So it's a question of over what time scale you are actually doing this averaging. And if you do the averaging at a very short time scale, corresponding to the collision of the particles and things like that, then the local density is not a very useful thing to look at, because it will basically, just as I said, if you look at just one configuration, the local density will be basically a delta function at the points where the particles are located, and you'll get something that has a bunch of delta functions at some points in the space. But if you're doing a thermal averaging, then you are not looking at a particular snapshot. You are looking at many such snapshots. And then the local density can even be defined at a particle scale. In the sense that if you look at a small volume, where the volume is basically the volume per particle. So you have a big volume, and then let's say capital V, and then you have n particles in that. So you can define V divided by n, which is volume per particle. And even at that scale, you can define a local density if you are not just looking at one or two microscopic configurations, but a very large number of microscopic configurations through which the system evolves as it's evolving in time. So, of course, it doesn't make much sense to talk about density at a scale which is lower than the size of a particle, but even the particle separation length scale, one can define the density, not for individual snapshots or configurations, but for as an average over a very large number of configurations that the system goes through, even for a very short time interval.
With that question being answered, we have now reached the end of the first session of the lecture series, and it was indeed an insightful one, and I express my gratitude to Professor Dasgupta for it. We will be continuing the lectures tomorrow at the same time, and I request all the people who have joined in today through Google Meet or YouTube to be with us tomorrow as well. Thank you, everyone. Hoping to see you all tomorrow. Thank you, sir.
Okay, thank you very much. So I'll be there tomorrow.
Yes, sir.
Thanks, Chandan.
Okay, thanks a lot. So I hope it was to the appropriate level and all that. I'm not
Yeah, it was excellent.
Wonderful lectures, Chandan. Yeah.
Bye.
Okay, I'm happy to do that. So I'll sort of
This is
continue. Ah, okay, yeah, thanks for tuning in.
Yeah.
Okay. Bye.
Bye-bye.
Okay, bye.
Great.